Hello, thanks for watching this video and studying math with me. This video, instead of just solving differential equations, we're going to talk about modeling differential equations and then solving them. This is a continuation of the work we did in Chapter 3 where we talked about modeling first-order differential equations, but now we're going to be modeling second-order differential equations. And modeling second-order differential equations is going to be the subject of one of the problems in your take-home suite for the final exam. I do suggest that what you do is take your time with this video. Feel free to use the stop, rewind, and buttons, and also look at the material that I have put in course collateral, which is pretty much a copy of these slides. And we're going to be studying mechanical vibrations, but much more than mechanical vibrations, because these equations really apply to so many things. Now here is the general model that we're going to be looking at. It is important that you realize that x is going to be taken to be positive going down and negative going up. And there are reasons for that choice, but you're just making that convention. We will start with a spring. Here is the spring that is not stretched at all, and the spring has a spring constant called K, which is associated with the how the spring responds to force, and that's Hooke's law. And we'll talk some about that as we go forward. We attach a mass to the spring, which makes it goes down a little bit, and here it is in what we call the equilibrium position. We're going to call that x equal to 0, like we have over here, but that is the force due to gravity is exactly balanced by Hooke's equation, and so that is equal to 0 as we go forward. But then we're going to talk about displacing this mass, like pulling it down, for example, or pushing it up. Then we're going to let go, and it's going to go back and forth and back and forth. The distance in the equilibrium position is called L, but whenever we put the, over here, this equilibrium position, but when we put, that's the unstretched spring, but when we put the weight on it, it goes down by another S, and that in fact is what's called the equilibrium position, x equal to 0. Then we pull down, it'll be x, but up here it'll be L plus S, corresponding to the equilibrium position. Now what we're going to do is look at Newton's second law with this. So the net force, which is ma, or m, the acceleration is going to be the second derivative of x with respect to t. It's going to be the sum of the forces. So we have the forces associated with Hooke's law, which we're balancing with the forces of gravity, and whichever one wins is the net force. But we make note of the fact that this portion of this is exactly equal to 0 because of the equilibrium position that we chose. So what we really have is m dx dt, and that's actually the second derivative of x with respect to t, is equal to minus kx. So if we simplify it that way, and we make the substitution of omega squared equaling k over m, we get this differential equation, which is one that we know well, because this is the differential operator d squared plus omega squared is x is equal to 0. And this is called simple harmonic motion, or in another vocabulary, free undamped motion. And we know how to solve that. This is one of those equations that you've sort of memorized, and we know that x of t is going to be c1 cosine omega t and c2 sine omega t. The period of this motion is t, and t is 2 pi over omega, and this is the number. T represents the time in seconds it takes the mass to execute one complete cycle of motion up and down. And related to the period is a thing called the frequency, and the frequency is the reciprocal of the period, as you've done before. And the number associated with the system, the spring constant, and the mass that you're attaching is known as the natural frequency. And we'll talk about that in a bit. So our goal is to find the equation of motion. Now I am going to mention quickly that whenever we have our previous solution, let me go back to it, our previous solution that was this, it's difficult to know what is the amplitude of that motion when we graph it. So often what happens is it's convenient to convert a solution in the previous form into the solution that looks like this, and we're using a trig identity. and this is something you probably studied in your trig course, and that's called a phase angle, and we're converting it to a single trig function. Now, in this equation, a is going to be the root mean squared, or it's going to be, you're adding c1 squared plus c2 squared from the general solution and taking the square root, and the phase angle is defined by the tangent of that is equal to the ratio of c1 over a, and the cosine is going to be c2 over a, and so this is going to be the inverse tangent of that. Now you should be aware that some instructors in science and engineering prefer to express this in terms of cosines. I studied at Purdue, and in fact these notes are going to probably use this, but your book will use both of them, and so that will be useful. It's time for us to maybe start doing an example then. So suppose we have a 16-pound object stretches a spring 8 over 9 feet by itself. There is no damping and no external forces acting on the system. We'll get to those later. The spring is initially displaced 6 inches upward from its equilibrium position and given an initial velocity of 1 foot per second downward. Find the displacement at any time t. So let's go through and talk about this solution. The first thing we're going to do is find the mass of the spring. And the mass of the spring is taking the pounds, which really is a unit of force, divided by the acceleration of gravity, which I'm taking to be 32, and that's going to be 1/2, and that's going to be a slug. The other thing that we're going to have to do is we're going to want to know what's the spring constant, and the spring constant is it's going to be K times that L is equal to mg, and so when we solve for K, we're going to have 16 divided by 8 over 9, and that's going to give us 18. So now we can write our equation. This is going to be ma, and we'll move this 18 over to the other side, so this is going to be 1/2 u double prime plus 18u is equal to 0, and we have initial conditions that are these based on the problem. Note the sign convention does come into play about where is plus and where is minus. So the solution to this problem is well known to you. U of t is going to be c1 cosine 6t plus c2 sine 6t. And whenever we plug in the initial conditions, we can find out what those coefficients are. So we end up with minus 1/2 cosine 6t plus 1/6 sine 6t. Now to convert this then to a single cosine, what we do is we find the amplitude, which is going to be the sum of the squares of those coefficients, and we get that it is the square root of 10 over 6, and we are going to use calculators on this because we're pretending to be engineers, so that is 0.52705, and then we want to find phi. Now phi is the arctangent of, and this is the ratio I talked about before, and so when I do that ratio and find the arctangent, again using my calculator, I get this is the arctangent in radians. But we have to be careful about this because the range of the tangent, the arctangent goes from minus pi over 2 to pi over 2, but we have to figure out in what quadrant really is this. So it could be exactly this number, or it could be that number plus pi being in a different quadrant. And so here I'm taking pi to be 3.14 and change, I get that. And so we have to figure out which one of those two is it. Well, from the trig identities, and also from our initial conditions, we know that C1 is equal to A cosine phi, and that means cosine phi has to be less than 0 because the C1 was minus 1/2. Similarly, C2 is A sine phi, and that means that is greater than 0. So what we know is that we have a we know that we're in the second quadrant rather than the fourth quadrant, and so that tells us that this is the value we want to use. So now we can use the A and the phi that we had, and we can write down the solution to the differential equation, which you see here. I will move that up just a little bit so we really can see it. And so we have u is equal to that A times the cosine of that, and we can now graph it. And here is a graph of that. And we can see that if it's undamped, it's going to keep moving on forever and going up and down like that. In fact, here is what we're really talking about is we have the spring going up and down like that, the mass, and so we get an oscillating thing like that, and that is called simple harmonic motion. Now, there are all kinds of variations that people will do on this. Some people talk about aging spring, and there you're going to replace the spring constant by one that is a decreasing function, like an exponential there, and it turns out you have to do infinite series solutions to that, chapter 6 techniques. Another thing that can happen is they can say that you're in an environment where the temperature is rapidly decreasing. That changes the way the spring behaves. Here we say it's kT, and if we put that into our equation, we get Airy's differential equation, which again we solved earlier. And so I'm going to pause here on this first video, and that covers at least one of the examples we want to choose. Thanks.